grad students come in, they've never taken FEA before.
Yeah, I'm like, the math part won't be hard.
Mhm.
It's just I'm here for the experience of going through it.
Gotcha.
So
We will do more ANSYS for sure.
yeah,
Than what we did in 541. So I think you went for that part.
I'm so I figured I started yesterday the project. I'm like, this looks very familiar.
It's literally exactly the same.
It's the same exact project. I figure I'm not here just for an easy grade. I'm here to learn it, so I'm still going through it.
Yeah.
Not just going, okay, here's these screenshots and let's retype this up.
No, I know, I know. Yeah, kind of the unfortunate thing is that I teach all the FEA courses here, and so there's a lot of overlap between them.
Yeah.
Mostly just because we don't enforce the prerequisites between them. So, some people are coming in, they've taken 410, they haven't taken 410, they've taken 540, 541, so makes planning a kind of a nightmare. But actually, this upcoming year, just because I think we're going to start to offer 410 more often now. So, we're offering it this summer, we
Yeah.
offer it in the fall and the spring. I think we can actually start to enforce that prerequisite. So I can actually do some more interesting stuff at the 500 level courses. But unfortunately, that would be next year, not this year.
Yeah.
Well, you know what? I think if there is someone on staff that would know something about viscoelastic materials, it would be Dr. Shinyi Wang.
Okay.
Dr. Wang, because her expertise is in materials actually. So
Yeah.
so her one of she had a student that just defended their thesis about basically the propagation of microfracture materials. Now that is a different area
Yeah.
of material science, but I would ask her and I would ask Dr. Su as well, because they're both in materials.
Okay.
Yeah.
Thank you.
Mhm.
Good to know.
I brought treats.
Oh,
It was for a Team Rover meeting, but
Oh,
there's
wow.
obviously plenty left over, so I'm gonna give them to the class.
oh, wow, thank you so much.
Absolutely. I usually do it throughout the regular semester, so I was like, why not do it this summer too?
Oh, very nice of you.
Thank you, thank you.
You're right, yesterday it might have been more cold, but I think when everyone heard there's a Zoom option, they're like, ooh.
Yeah. Yeah, I was downstairs in 42 testing metal for Dawn
Oh,
all
okay.
day. I'm the new lab assistant, but I think it's a preparatory role to potentially take over what Dawn's doing when he
Okay.
retires.
Oh, great.
So I was like, all right, I can do that.
Nice, nice.
Yeah, and then I still have not met with Dr. James, but the more information I'll have about that program, absolutely, especially if this all ends up going through, so I'm here for a while.
Yeah, yeah. Oh, great, great.
Thank you.
Got you. Did you make these?
Yeah, so the top ones was actually my wife, and
Oh.
the bottoms is me.
Okay.
Stones were good.
Yeah, stones are
Oh my goodness.
yeah.
I'll try one of each.
Please. Free treats if you don't want some. They're for anybody. Brought them for Rover and we got extras.
Oh wow, that's really good. I need sugar to get through these 3 hour lectures. It's a it's a marathon.
Oh, next. No. It came on a cut. Shouldn't fall. Oh, yeah.
Start with it and getting it set mesh.
Oh, what?
If I leave, it's because my computer died. I thought it was charging. It's not.
Quadro.
So, but I will get back. But I do want to stay for as much as I can.
Okay.
But then, yeah, if it does, I'll run and then I'll log right in.
Well, we're gonna do the activity in the second half, and so actually the ANSYS is working on the lab computers here, so we
Okay.
can do it on the lab computers. Perfect. Yeah.
What time? Does it take USB-C?
No, it's got that big old beast thing.
But if it has USB-C, it should be able to charge through it.
Oh, really?
Yeah, at least that's how Microsoft does. If you want to try these,
Yeah,
please. This thing, I can charge everything with.
Yeah, my old one, it would do C, but this one. Oh, it's on that side. Excellent. Thank you. I'll just sit there until it's like that.
So. Are you running it on a Mac?
I am.
How'd you do that?
So I'm using a program called Parallels.
Oh, it's working for Parallels?
It is. So I got Parallels back for SolidWorks. And yeah, and the latest edition, it's great because I can actually dual monitor both
Yes.
of them and it'll cross in between and it'll working out really great. The only thing it doesn't do is share the actual save section on the hard drive. It keeps one Windows and one Mac.
Yeah.
So the pain is like if you create something in SolidWorks, I can't just put it on my Mac and so I have to email it to myself. But other than that, yeah, it works really well.
Also, there's like prerequisite problems, like downloaded or something.
So there is, I didn't have any.
3 o'clock, I sorry. All right, so let's get started. So welcome to day 2 of EGME 410. Today we have our first ANSYS activity. So we are gonna do that in the second half. So first half, just because we're doing ANSYS activity 2 in the second and on the second day. I thought might as well let's talk about meshing first, just because I think that'll give a bit of context in terms of what we're going to do in the activity. So we'll do that for the first half, and then the second half we'll do the activity. So I did test it today. I tested on the podium computer. Our IT guy tested on the lab computers out there, so it should be working. And so for those of you that are joining on Zoom, of course, hopefully you were able to install ANSYS, the student version, yourself, and so you guys should be able to follow along. I did update the due date for this activity. Originally, it was supposed to be due tomorrow, just because I was going to do ANSYS activity 2 tomorrow, but just with just kind of the delay, I shifted everything back. So activity 1 is now going to be due this Sunday, just so you guys have the weekend to do it, and then we'll start next week first thing. We'll do ANSYS activity 2 from there. Okay. All right. So that's the plan for today. That's about it. Got any other announcements? Are there any questions I can answer before we get started for today? Okay. All right, so let's go ahead and get started. Okay, so today's lecture is going to be about meshing. And so today we're going to go over what I call meshing basics. Right, so today is not going to be the first. Today's not going to be the last time we talk about meshing. Like I mentioned yesterday, meshing is probably it's hard to say that it's the most important, but I would say it's the most unique portion of finite element analysis. Probably the portion you haven't thought about ever in your previous classes. Tomorrow we're going to go over boundary conditions and material properties. Which for the most part you've kind of seen in different forms in your other classes. So meshing, I kind of want to spend a bit of time on quite a bit in this class. Okay, so first let's kind of define meshing one more time. So when we say we want to mesh our geometry, we're basically looking to break up our geometry into a bunch of tiny, simpler shapes. So what you're going to see is that, and you'll see this when we do our activity later, it literally looks like you take your geometry and you just kind of superimpose some graph paper on top of it, right? So, visually, you'll start with, maybe a geometry that looks like this, right? So this is your, starting arbitrary geometry. It looks like a potato here. When you mesh it, we're going to take this and then, essentially kind of put a grid on top. So it's going to look something like And so the whole idea is that instead of analyzing one kind of complex geometry where it's very hard to solve our equations on, right? So because that complex geometry can have any number of different sizes, any number of different curvatures, right? Different edges, different surfaces. Instead, by meshing, we're instead solving our equation on lots of simpler geometries with a known shape, right? And so that's kind of the key. So one thing we're going to talk about today is that, when you are creating your mesh, right, you have to make a decision in terms of what element shape that you want to use. And your choices are not many, but they are consequential. And so you can either choose, so for the activity today, we're going to do a two-dimensional simulation. So you can either choose a triangle or you can choose a rectangle, which I know doesn't sound too exciting, but it does make a difference. Right? And there's other features of the mesh that are going to make an impact on your simulation results as well. Okay. So the mesh is one thing where if you're not careful, it can kind of, get away from you a little bit because, if you're using ANSYS just as a new user, ANSYS provides a way for you to generate a simple mesh. And so you can just use all the default settings within ANSYS and generate a mesh. And it will work. You'll be able to get a result from it, but more times than not, it's not going to be a result that's reliable. And we'll talk about kind of why that is throughout today. Okay. And the nice thing about these kind of longer class sessions in the summer is that you'll actually see that applied right away. So we'll talk about the mesh first half today. Second half we'll do activity, and we'll get to see the mesh in action in terms of what the different settings actually do. Okay. Okay, so the plan for the first half today is, we're going to go over just all the just very basic meshing settings. We'll talk about what they do to the mesh and then what they ultimately do to your simulation results at the end. Okay. Any questions on this so far? Okay, good. Okay, so first, before we get into the really nitty gritty, let's talk about just what makes a good mesh in general. Because you can certainly make a bad mesh in finite elements, and then it's important. One important skill for you to know is to be able to identify what's a good mesh and a bad mesh. Okay, so let me just state it plainly first, and then we'll kind of dive more into what this statement actually means. So a good mesh is one that gets you an accurate and reliable solution in the least amount of cost. So I've kind of underlined the two dominant factors that will go into your mesh, right? So the first factor is just accuracy, and the second factor is cost, right? And you're going to see that these two are often counterbalanced with each other. Usually, if you want more accuracy, it's going to cost more. But if cost is a big concern, then you might have to sacrifice some accuracy for that as well, right? There is some nuance, of course, and so you can change the size, you can change the shape of the elements, you can change the order of the elements. So there are ways to generate more accuracy without necessarily increasing the cost. But this is the main trade-off that you have to think about when you are creating your finite element. Okay, so let's go through each of these one by one. So let's talk accuracy first, right? So accuracy refers to how well we are solving our governing differential equations. So remember we talked yesterday about FEA, being just a method for solving these, oftentimes partial differential equations that govern our physical behavior, right? So accuracy refers to how well we are solving these. So what do I mean by that? So, when we run an FEA simulation, right? One thing I neglected to kind of mention yesterday, and I realized that right after the lecture ended, is that FEA doesn't necessarily find an exact solution to our governing equations, right? FEA is, at its core, it's an approximation technique. Right, so we're not solving for exact solutions, and actually, depending on how we make the mesh, depends on how close we are actually going to be to that solution. Okay, and so the main factor for a mesh that determines accuracy is how many elements, or I guess more specifically, the size of the elements in our mesh. And so more specifically, the smaller your elements are, the more accurate you can expect your solution to be. So an analogy that I always like to bring up in this section here is, think about how we understand image resolution, right? So when you take a picture, so it's a little bit harder to explain now just because, I feel like phones nowadays have such good cameras, but kind of not too long ago, we would take pictures from our phone and they'd be a terrible resolution, right? It was not too long ago, where you could buy a TV that was only, maybe 480p, right? Or maybe, if you're on YouTube and the connection is not great and it has to kind of buffer, right? Maybe you reduce the quality to 480p. Right. And so what that P basically represents is the number of pixels that are on your screen. And so if I were to kind of draw this, right? Let's say this is your screen right here. So when you have a low resolution image, right, the size of the pixels on the screen are relatively big, right? And that's not actually 480. I can't draw 480 pixels on a screen like this, but you can imagine that if each of those pixels that I drew there were a single color, right? It's kind of hard. You're going to get a blurry image. Right, so let's say, we have this one is red, right? It's very hard to kind of pick out a sharp image from this. Whereas if you look at a higher resolution image, and so, I would say the bare minimum nowadays is 1080p, but it wasn't that long ago where 1080p was actually a big revolution. Now you can go up to 4K, which is insane to me. Right, so if you have a screen or your image quality or your video quality has a higher number of pixels, what that essentially means is that you have more pixels within your image to generate a sharper image, right? So I kind of regret doing this already, but you know, you can kind of imagine that all these pixels here are a lot smaller. So you can imagine that, you know, for an image like that, if your pixels are, you know, are much smaller, you end up with a much sharper, much clearer image. Usually that's one that's more appealing to watch. So for finite elements is the same, right? So the smaller your elements are, and just by association, the more elements that you have in your simulation, the more accurate you can expect your solution to be. Okay? So let me kind of give you a more kind of direct example in terms of what FEA is doing, right? So let me show you a one-dimensional example here. Okay? So let's say that we have a function. Right, so let's say that that black line right there represents the exact solution to our problem. So let's say we just have a one-dimensional ordinary differential equation. If we wanted to approximate this using finite elements, the accuracy of our solution will depend on how many elements that we have. Okay. So just naively, you know, let's create just an approximation with just one element, and we're going to assume that our one element here has a linear approximation. So one element approximation may look something like that. Right? Where on that one element, we're only able to have a linear approximation, so it just goes from the start to the end. Or at the end point, you know, our solution may match, but in the middle of the element, then, you know, we start to deviate from the exact solution quite a bit. Okay. But then our accuracy improves greatly when we go just from one element to two, right? So let's say that we make a second element where our second element intersects the exact solution right there. Okay. So in orange there, you can see we have a two-element solution there. Right, so you can see that we're getting closer, we're getting much closer to the exact solution in that case. And then we can even get even closer if we add another element. So let's say we do three elements, and so we have something like this where we're hugging the solution much more closely. Just like that. Okay. So the smaller your elements are, the more elements that you have in the mesh, you know, the greater you can expect the accuracy to be. Okay. Okay. Good. Any questions on concept of accuracy in FEA simulations? Okay, good. So you might look at this, you may think, you know, that's good, right? So then why don't we just make the elements as small as possible, right? So why don't we just make elements all this micrometer scale? Well, there's the other factor that gets into it. So let's talk about cost, okay? So when we talk about cost for a finite element simulation, we're not necessarily talking about financial cost. Although eventually it does end up being financial cost, but just, you know, what we experience as users, cost refers to the amount of computational time and the amount of memory that it takes to run a finite element simulation. It's primarily time, right? And so the main cost that we experience as users is just the amount of time that it takes. But there's also computer memory, power, electricity, things like that as well. Okay. Question?
Yeah, so makes sense that the more elements, the more kind of can approximate the curve. We're talking about like the mesh, looking, like the body and the surface kind of the.
Mhm.
So when we are looking at like a curve, is that like, it makes sense from the mathematical like perspective, but what I'm kind of trying to understand, like, so if you have a flat plate, right, the amount of elements you need on that compared to someone that has some sort of curvature, like, might be less, right? I'm thinking intuitively.
Not necessarily. It depends. It depends on the nature of the solution that you're trying to find. If it depends on the solution, and so and we'll talk later on in the session, what aspects of the solution you may want to look at to increase your mesh density. So one thing, well, I'll give you a brief preview right now. So if you observe in your finite element solution that you have very sharp solution gradients, and so your solution is changing very rapidly in a short period of space, that might give you a hint that you may want to refine your mesh a bit. But if you have a very slow varying solution, like there's not a lot of changes that occur in a short period of time, your solution's probably already converged, and so you probably don't need more mesh elements in that case. So geometry does play a factor, and so complex geometry does usually make your solution do some more complicated things, but that's not necessarily the only factor that requires a fine mesh. It depends more on the quality of your solution.
So the differential equation that you have here, that's like the geometry is just one part. It's not like the thing that's defined.
Yeah, so this curve is a solution. Yeah, so I made no reference to the geometry in this. Okay, so what tends to happen when you have a mesh is that the more elements that you include, the smaller the elements you have, it's going to cause the cost to go up. And intuitively, that's what we think about with image resolution as well, right? So the higher resolution your image is, the more memory it takes up in your, on your computers or on your phones, right? So a very low quality images maybe only take up just a few kilobytes, but if you have a photography quality, picture, that's going to take up a lot more space. Okay. Okay. Now I will say that for all the simulations we're going to do in this class, you're not really going to feel the effects of cost just because of the licenses that we have for ANSYS. Okay. And so what I mean by that is that the student version of ANSYS. So if you install ANSYS on your own personal computer, ANSYS actually places a hard limit in terms of the number of elements that you can use for your simulation. So for ANSYS Student, the one that you downloaded from the website, I believe the limit for that is 64,000. Although I haven't checked in a couple of years. Sometimes they raise it every now and then. The licenses that we actually have on the lab computers in this room, and technically in the other room as well, we technically have a slightly better license. I don't know what the limit for that one is, but I know it's greater than 64,000 because I know I've seen it. I want to say it's around 100,000, but I've never actually pushed it to really find it. So all that means is that you're never going to have a simulation that takes more than probably 5 minutes. 5 minutes is probably the maximum that you'll probably experience in this class. Because 64,000 honestly is actually not that much in the grand scheme of things. I would say most practical applications for finite elements, you're probably running simulations that have, at the very least 500,000 elements, probably in the order of the millions, okay? But for everything that we're going to do in this class, in terms of the activities and the projects, 64,000 is more than enough. I don't think you're going to need more than, 30, 40,000 for most things in this class. But just be aware of that, okay? So when I talk about cost, I think some people look at me like I'm crazy, say like, oh, that was a very expensive simulation, but it maybe only took like a couple minutes. But there are simulations that are out there that I've seen you use up, thousands and thousands of computer processors, and the simulation would still take them 2 weeks to finish. So cost can really get out of hand if you're not really careful. It's just that for this particular class, because of the limitations that we have, it's not something that that it's hard to kind of get an appreciation for that, for the complexity of problems that we're looking at. But I did want to mention it just because it is an important fact. Okay. Any questions on this so far? Yes.
Was like a real world example that maybe you've experienced where you had to like take cost into consideration?
Yeah. So in my line of work, I work on fluids a lot, and so a notoriously difficult fluids simulation that's to run is a turbulence simulation. So turbulence, one way you can simulate turbulence is to use a method called DNS, which is direct numerical simulation. Those meshes will have anywhere close to hundreds of millions of elements, and they're running it for long times. And so I've run into this personally just because typically those simulations aren't run on your personal computer; they're run on high performance computing clusters, and those clusters are shared between lots of different people that want to do work on them, just because they're expensive to build. And so I've run into issues where I need to run my jobs for my own work, but the turbulence people are using up 80% of the system, and I can't get my jobs in. So yeah, that's one, just I think, just example off the top of my head. Any kind of molecular dynamics simulations are also very expensive as well. So anything where you're simulating on the order of like the molecules or the particles, those can get very expensive. Okay. So these two factors, accuracy and cost, are in direct competition for each other, because in order to get an accurate simulation, we want to add more elements. But in order to have a cheap simulation, we want to have elements. We're going to take elements away, right? And so there's always a sweet spot, in between these two, and that's what makes a good mesh. So how do you know? How do you know when you have a mesh that's fine enough for an accurate solution and one that doesn't cost too much? Well, cost is easy to determine. If your computer is locking up for a couple of hours, probably it was a little bit too expensive. But how do you know when you have an accurate simulation? So later on in the semester, once we kind of start talking more about the projects, we're gonna learn a technique called a mesh convergence test. So mesh convergence test is something that you can do to basically show or determine whether your mesh gives an accurate enough solution. Right, but we'll get to that kind of in due time. So, for the first three ANSYS activities that we're going to do in this class, we're going to introduce just the basics of ANSYS. But then, once we start to get, more advanced stuff in order to prepare, and you guys are preparing kind of more professional reports on finite elements. This is something that in my opinion, I think is a required aspect to any kind of professional work. Not just with finite elements, but any computation method, whether you're running CFD, finite volumes, finite elements, finite difference. there needs to be a mesh convergence test. Otherwise, there's no way we can test, we can trust your results. Okay. So element size, even though that's certainly not the only feature of a mesh that's important, I would say that's probably the most important aspect of the mesh. Okay. Let's talk about some of the other aspects as well. So let's talk about element shape. All right, so besides the size of the elements that we can choose for our mesh, like I mentioned before, we can choose the shape. Okay? And the shape is important because kind of the whole backbone of finite elements is that we're relying on the fact that our mesh is comprised of these elements, and we know what the shape is beforehand. So we know how many corners are going to be in the shape, we know how many edges are going to be in the shape, and once we get to 3D, we know how many surfaces are in the shape as well. So for most practical situations, and these are the only two options that ANSYS gives you. Not that these are the only two options ever in finite elements. If you use kind of more advanced codes, there are more options. But the two that ANSYS gives you, I would say, are going to be good for 99.9% of situations. And so I break them down into two different categories. So there are what I call triangular elements. Right, so there's a 2D and a 3D version of a triangular element. Okay. And there are rectangular elements. We have a little bit of a table going on here. So the triangular elements share certain properties, both 2D and 3D. We essentially kind of treat them the same way. Same thing for rectangular, right? And so, the distinction for you guys to know here is the difference between triangular and rectangular elements. Okay. So in 2D, a 2D triangular element is actually just a triangle itself. So pretty simple. Triangle just has 3 vertices and 3 sides. In 3D, a triangular element is called a tetrahedron. So if you've never seen a tetrahedron, the tetra stands for 4, and so a tetrahedron is essentially a 4-sided pyramid. Right? And so those two edges in the back are connected. So it has 4 vertices and 4 sides to it. Okay? If you've ever played Dungeons and Dragons, a tetrahedron is just your standard default. All right, so for rectangular elements, a 2D rectangular shape is a rectangle. Big surprise. But oftentimes, when we talk about a 2D rectangular element, those are often referred to as quadrilaterals. It's a bit more of a specific term just because in order for a rectangular element to work, the two opposing sides have to be parallel to each other. Okay. All right, and then the 3-dimensional rectangular element is called a hexahedron, which is just a fancy name for a box. It's your good old standard Amazon package. But it's given the name hexahedron because hex stands for 6, and so your hexahedron has 6 sides to it. Okay, 6 sides, 8 vertices, and 12 edges. Okay, well, like I mentioned before, the difference between 2D and 3D are not that big a deal. It kind of just depends on the geometry that you're looking at. Most FEA simulations that you're going to be doing are 3 dimensions, just because we live in a 3-dimensional world. The main distinction that you have to kind of know is when to use triangular elements and when to use rectangular elements, okay? So let's talk about that a little bit. Okay. So triangular elements. Triangular elements have one very important and useful property, and that's called the simplex property. And what that means is that, you know, you can use triangular elements to mesh any geometry without fail, okay? Okay. So if you have a two-dimensional space or a three-dimensional space and you want to fill it with these elements, right? It's a lot easier to do so with triangular elements. Okay, so you're much less likely to have your mesh fail if you choose triangular elements. Okay, so what does that mean? So that means that if you have a geometry that you know is going to be very complex and has a lot of complex geometrical features, you know, you may want to try meshing with triangles first, right? Just because you're more likely to get a mesh in that situation. And the reason why triangular elements have this simplex property is that a triangle is not really a symmetric looking shape, right? So there's, you know, if you kind of look at it from this perspective, right? And so we kind of draw kind of a line that's kind of going like this, right? So if you look at the top half of this triangle, the top half is skinny while the bottom half is more wide because it has more vertices. And that actually helps a lot. And so if you ever have any kind of weird corners or weird spaces within your space, then a triangle it's much easier to fit a triangle into those spaces than a rectangle. Okay. Now the downside to triangular elements is that, you know, because they do have that kind of lopsided shape, it's not particularly great at filling space efficiently. And so what that means is that if you were to mesh with triangular elements, you know, you're going to end up with many more elements in your mesh compared to if you use rectangular. And as we just kind of finished talking about, the more elements that you have, the more cost you're going to incur in your simulation as well. Okay. And so you may end up with a more expensive simulation, or even just more practically for this class, you may end up with a simulation you can't even run because you're going to overrun the element limit count for our academic version of ANSYS. Okay. So triangular elements, they're reliable. They're going to get you a mesh, which is not underrated. Let me tell you. So, but you know, if you can avoid using them, if you can mesh with rectangular elements, that's usually a bit better to do so. Just because rectangular elements have better space filling properties, they have better solution properties as well. Okay, let's talk about that. So rectangular elements have much better space filling properties. So they can fill space a lot more efficiently. And so filling space more efficiently means that you get lower element counts as well. Oh, question from the chat. So question says, could you mesh, can you mesh with both rectangular and triangular elements to analyze part? Yeah, you can. So one thing we're going to talk about right before we do the activity is you can do mixed meshing. And so sometimes, for a particularly complex geometry, you can mesh one portion of your geometry using triangular elements and another portion using rectangular elements. And that actually goes for other aspects of the mesh as well. So you can actually do a more refined mesh in certain areas and a more coarse mesh in other areas as well. So you're definitely not limited to a certain setting for an entire geometry. A lot of times it does actually pay to, mesh with different settings in different places. Yeah, for sure. Usually you don't want to mix too much. Like you don't want to have just an area that has both triangles and rectangles all mixed together. Usually you want to limit it to a particular region. So rectangular elements, they fill space more efficiently, and so that leads to lower element counts. One thing about rectangular elements too is that they give you better accuracy properties per element, right? And so one rectangular element has better solution properties than one triangular element. We'll go a bit more of that, I think, probably after activity 2, so probably middle of next week. What I mean by that statement, but you'll see that the shape function for rectangular elements has more terms in it, which gives us better properties. Okay. Now the downside to rectangular elements is that they're not as flexible as triangles, and so you're going to run into more meshing errors with your rectangular elements. Okay. You're going to receive a lot more errors when you do a rectangular mesh. Okay. And because of that, rectangular elements, they're best used for situations where your geometry is a little bit simpler, just because it's in those situations it's easier to get rectangular elements into there. Not that it's impossible to get rectangular elements to work for a complex geometry. You do have to kind of fiddle with it quite a bit. And so, I think probably by the end of the class, you guys will have enough experience to know how to finagle with the settings to refine the mesh in certain areas. Maybe you add a smaller mesh size and maybe you depress certain features, but it is more difficult to use rectangular elements. But your prize for doing so is that you get a better quality mesh with less elements and better solution properties. So, try to use rectangular elements if you can, but for a lot of cases with complex geometry, it is difficult to use. And I will say that even though the way I present this makes it seem like triangular elements are not great, I will say that all the work that I've done just on an academic and research and professional standpoint, I've always used triangular elements. Just because the geometries I work with just are naturally very complex, and so there's nothing wrong with triangular elements at all. It's just that you kind of have to know the limitations and have to kind of know that you probably need a little bit of a finer mesh usually with triangle elements in order to get your good answers. Okay, so that's the difference between these two. We'll get a chance to kind of try both of those in the activity today. Any questions on element shape? Yeah.
So somebody asked, we can do rectangle. So you also kind of just shading areas like a little more density.
Oh yeah. I mentioned that. So you can have different element sizes and different well, and that's called refinement. Yeah. Okay, and so while we're on the topic of shape, let's talk about skewness very quickly. Okay. So skewness refers to the one way to kind of say how ideal your elements look in your mesh. Or I guess maybe more accurate way to say the skewness describes how much we deviate from the ideal shape of the elements in our mesh. Okay. So every element, whether we have a triangle element or a rectangular element, has an ideal form that in which it performs best. Okay. And the form is as close to the way I describe it, as close to equilateral as possible. And so, you want a form where all the sides of your element have the same size, all the interior angles of your element have the same value, and so on and so forth. Okay. So for example, if we have a triangle, right? The most ideal form from a triangle is for it to look something like this, right? No, it's not perfect. I didn't pull the ruler out, but you want it so that the all the sides are approximately the same. All right. But what can happen sometimes, and some of this is unavoidable, right? And so it's unavoidable that you're going to have some mesh elements that kind of look kind of wonky. But as your mesh tries to kind of fit into kind of the small corners and kind of awkward areas of your geometry, you may get elements that become very skewed. Okay. So for example, right, you may get a triangle that may look something like this, where it's very kind of squished. So some of this is unavoidable. And so, you can't, it's impossible to get perfect elements everywhere unless you're just literally simulating a triangle or a square. And so if your geometry has any kind of complexity, there's going to be some elements that look like this. Okay. But generally, the more elements that you have that kind of look more skew will lead to a poor quality solution. And so, in fact, this is the term, the way that ANSYS calls this, we actually refer to this as the mesh quality. So quality is something that you could actually check within ANSYS itself to kind of check and see how the quality is. Okay. Now I will say that the meshing algorithm that's used within ANSYS is actually very good. It's actually proprietary, and so that's actually something that they don't share with people. But I will say that I've had some of my grad students actually create a mesh within ANSYS but then actually exported to another solver that has a bit more features that I like, just because of how good the mesher is within ANSYS. That's how good it is. So I would say that, for the most part, ANSYS will give you a good quality mesh. Granted that, your selections for the size and the shape are good choices. Okay. But even with that, it's inevitable that you're going to get some elements that are poor quality. That's just how meshing is. So there's always going to be some, right? So I think, I don't think we don't do it for this activity, but, for activity 2, we'll actually start to look at the mesh quality metrics within ANSYS. And so you're always going to have some poor quality elements, but, don't panic. That's just how meshing is. It's not necessarily the fact that you have poor quality elements. It's more the amount of quality elements that you have. And even if you have poor quality elements, the fix is usually pretty simple. Usually if you have poor quality elements, that tells you that you probably need to refine your mesh a bit more. Because if you're able to refine your mesh, then your mesh elements can be smaller. They're more likely to kind of hold this more ideal shape rather than have to kind of skew themselves to fit into the corners of your geometry. Okay. Okay, so we're not going to look at mesh quality for this first activity, although you're certainly welcome to, but it's not going to be part of this of the requirements for the first activity that we do today. Okay, any questions on that? Okay, all right, so we've gone over mesh size, we've gone over mesh shape. The last factor for the elements, and this I would say is probably the most invisible factor, it's one that you can't really visualize, is the element order. Okay. So the element order, what this refers to is this refers to how accurately we want our FEA elements to approximate our solution. Okay? So overall, we have a sense of accuracy in terms of how our overall solution matches with our governing equations, right? And that is determined mostly by the size and the shape. The element order, it really kind of governs how much on a per element basis, how accurate we are. Okay. So I know that statement is a little bit vague, and so let me kind of give it a bit more detail here. So for element order, we have two different options within ANSYS. We can either have a linear element or a quadratic element. Okay. Which might seem kind of strange terms when you think of finite elements, but once you kind of understand kind of what they refer to, it makes sense. Okay. So for a linear element, what the software or what the FEA technique is assuming is that within our element itself, our solution is going to vary according to a linear polynomial. Right, so I'm gonna write down a one-dimensional linear polynomial, but just know that, of course, we're applying this in multiple dimensions as well. Right? So a one-dimensional linear polynomial, as generic as it comes, looks something like this. Okay. Right, so linear refers to the power of I would say the exponent of the unknown variable here, which is x, right? And so a linear polynomial has an exponent of 1, okay? And so that means for a quadratic function or quadratic element, the variation within the element is then assumed to be a quadratic polynomial. And so a generic one-dimensional quadratic polynomial looks something like this. Right, so the main difference between these two is that the quadratic polynomial has that extra x squared term that the linear polynomial does not. Okay. Right, so this is kind of the main difference. So that extra x squared term is not free, and so it does take a little bit of extra cost to compute that. Okay. And so the choice of whether you're going to use a linear or quadratic element kind of goes, it's very similar to our discussion of element size. And so it kind of depends on how much accuracy you want versus cost. And so the linear element generally is going to be cheaper. But it's going to lead to a less accurate solution, or I should say on a per element basis, it's not going to be as accurate. Whereas the quadratic elements technically are more expensive to compute, just because there's just more terms for it to compute. But you do get something from this. You do get better accuracy. So that's generally the trade-off. But I would say that for most of our cases here, and this is probably the only section of this class where I will kind of say this, just because ANSYS makes it so easy to select quadratic elements, and the benefits are just so great for quadratic elements. 9 times out of 10, you're going to pick quadratic elements for your simulations. In ANSYS, there's really not a great reason to pick linear elements. There are niche cases to pick linear elements if you're looking at fluids. If you're going to run a fluid simulation within ANSYS, there's the stabilization just works better under linear. But for a structural simulation, for a thermal simulation, there's really no reason to not to pick quadratic in most cases. In fact, specifically for structural simulations, there are specific issues that can happen with linear elements. Something called shear locking, which we will discuss sometime next week, which is not an issue in quadratic elements at all. Okay. The reason it's kind of such an obvious choice is that ANSYS kind of does the hard work for you. Quadratic elements, although they're very powerful, are very difficult and annoying to implement in code. And so, if you were to write your own finite element code and use quadratic elements, you would see very quickly that it's not an easy task at all. But ANSYS has done it. ANSYS has done it, and they've made it very easy for users to select that. And so, most of the time, quadratic elements are good to select within ANSYS. That's part of what you pay for in ANSYS as well, is for them to implement something like this, which is normally very difficult. But they just make it a very simple option for you to select. Okay. So for most of the activities that we're going to do actually, for all the activities we're gonna do, you're gonna pick quadratic elements, just because the ANSYS kind of makes it that much easier, okay? Okay. Any questions on this? Okay, all right, so one last topic before we'll take a break is this aspect of mixed meshing. So I know a few people have asked about it already, but let's go ahead and talk about it formally here. Okay. So we've talked about all of these features within meshing, and this, of course, is not everything at all, too. This is just the absolute basics in order just to get started. But even just with the basics, you can see there's a lot of degrees of freedom. There's a lot of decisions that you have to make in terms of how you want your mesh, right? Choosing the size of the element, choosing the shape, choosing the order. And so just like a few people have asked already, a lot of times it's beneficial to use different mesh settings within different regions of your overall geometry. Because remember the overall goal for a mesh, right? And so, the mesh, we're trying to get the most accurate solution for the least amount of cost. There's going to be, for more complex situations, there are going to be regions in your geometry that have a more, I would say, complex solution characteristic versus others. And so, if you really want to make good use of your resources, good use of your mesh elements, you want to kind of give the most attention or give the most mesh density to those regions. Whereas, you can take them away you can take elements away from other regions where the solution may not be that exciting. Okay. So let me give you an example. And so you actually see this in about 30 minutes when we do our activity, right? And so for our plate with the hole for activity 1, and so we have our rectangular plate like this. We have our hole in the middle. Okay. So what you're going to see when you run the simulation is that within the regions around the hole, right, particularly, this region here, these regions here, okay, what you're going to observe is that the von Mises stress or the mechanical stress and those regions are going to be much higher compared to other regions within the plate. Okay. So usually areas of stress concentration are areas where you want to have the most accuracy as possible, right? Because those are going to be areas where, generally you expect your part to fail in those regions because that's just where the stress is concentrating. So you want to make sure you get the answer there correct. And so those are excellent candidates to add what's called mesh refinement, where we make the mesh smaller, have smaller and smaller elements in those regions in order to get the accuracy just right. Okay. And the opposite is true, of course, as well. And so let's say that you are simulating a geometry, but there's going to be a large portion of your geometry where not a lot is going to happen. Okay. So we give you a preview of activity 3, right? So ANSYS activity 3 we'll do at the end of next week. We're going to be simulating a freeway signpost. Right, so we have a signpost that looks something like this. It's a very poor drawing of one, but you can kind of see, right? And so once again, when you do the simulation, you're going to see there's a particular region where stress is going to concentrate, which is the region which is supporting the entire weight of the signpost, right? Which is going to be down here. Whereas if you look at the other regions of your signpost, right, particularly the sign, right, so the rectangular part, there's not really going to be much stress up there because that part is really only supporting its own weight, which is not much compared to at the bottom. Okay? And so that might be a good candidate to say, let's coarsen the mesh in this region, just because our solution's not really doing anything interesting in that area. Okay. And then let's take the elements that we save in that region and let's pack it into the region of stress concentration, which is down here. Another aspect that you may look at is you can look at the fact that our sign here is a very rectangular geometry. The sign is literally just a rectangle. Okay. Whereas our post, the column that's supporting this is a cylinder. Now, a cylinder, so this isn't the best example. A cylinder is not exactly what I would call a complex geometry. You could very easily mesh a cylinder with rectangular elements, but the curvature of a cylinder may give you some pause at first to say that maybe this is a geometry, it has some curvature, maybe it'll be easier for us to mesh this with triangular elements. Whereas the rectangular signpost, right, that's as rectangular as it gets, just because it's a giant rectangle. So, this will probably be very easy for us to mesh with our hexahedrons or our rectangular elements. Right, so mixed meshing, very, very common. In fact, ANSYS actually makes it very easy to do so, to apply different mesh settings in different regions. And that is definitely something you will make use of quite a bit. Maybe not for the first couple of activities, but as we start to do more complex things, as you guys do your own projects, the midterm project, final project, this is definitely something you're going to want to make use of in order to get the most out of your simulator. All right, any questions on this? Yeah.
Yes, so, not exactly on this, but, I'm trying to understand the difference between mesh quality and element order.
Mhm.
So like, I get that, with mesh quality, it's just kind of telling you how much, deviation you're getting from that ideal kind of triangle.
Mhm.
I don't understand how element order is different. Well, it's I get that there's linear, but like what exactly? I don't know. I'm trying to picture it. Like what it means.
Yeah, so element order refers to how the solution is approximated within the element itself. So element order has nothing to do with shape, whereas mesh quality is only based on the geometry of the element itself. So mesh quality is how the shape is formed in terms of geometry, but order is how the solution is approximated. Yeah, so they're kind of completely separate.
Does element order take like quality into account, or it's not?
They're completely separate. Yeah. Yeah, so you can have poor quality elements with a quadratic order, but mesh quality does not have any, it's not a direct impact on the solution. Mesh quality is just the shape of the element. Right, any other questions? Okay, let's take a 15-minute break, so let's come back at 25, and then we'll start our ANSYS activity from.
Yeah. Okay, that was like I tried getting it going. Problems about it too, like you, it's been forever, bro.
Oh, yeah.
And it is like, yeah, we gotta extract them. I think it's like downloading.
Well, it was done until.
And then. 96%. Oh my God. I have a scooter at home. Yeah, it helps, but I'm typically a week, so. Yeah. I was, yeah. But the weird thing is that. But it's crazy. Yeah. Yeah. Yeah, I just don't want it to get any worse, bro. So I'm like, what do you hope I should just be scootering around, but.
Don't thank me, it was Chris that brought it in.
Oh,
Thank him.
Oh, thanks to. Yeah, he wasn't there. I can. You did. You might really close. I got. So it's like what? 60 something like that? 50. I got up at 70. Essentially. Thanks, dude. Okay, I bet it. I saw it, you know, it wasn't good. Yeah, so you died at the qualification, bro. I was like, how did you think you died at the qualification? Or did you basically give me 7? And I was like, I show up to the classes, I asked the questions like everything. And we show up outside of class to do the extra work. The one that frustrated me. I wonder who. 10 out of 10. I know. I'm just gonna tell him. I think he already changed it because it's. Dude, you got the opportunity to take like just one of his quizzes. You could have got that. I know. That's exactly what I'm saying, and that's what I want to tell him. Because if I got an opportunity to your participation, that's 0.5 balls out of a local 88.5 to a 89.3 comfortable. Yeah. And total of please, I mean, very easy to have insurance. Don't say that. I want to change that. But I need to tell you, need to help me. Yeah.
There's a lot of people who are like.
So that's
in a small country, right?
a lot of things.
Maybe that's stupid, because Iraq had like 30.
Let's go. You gotta dig it.
And they still made it.
You change it? I think you changed it.
With the most qualified people in Italy.
But I
They had to do with talking
that's one of the opposite.
They didn't even have a hard group to vote for Paul.
Like, I got pretty finals, yeah. That's good. That's good. Doing classes.
It was in Norway.
He was like,
Oh,
yeah,
Israel, Estonia.
that would help to just get like. Yeah, because you get a 3, you get a 4.
Yeah.
Otherwise you get like 2.7 or something.
Yeah. So that's, I would, it's just like, just give me.
Yeah.
Is considerable.
But you bring it.
Hope that I probably I was like, you agree.
Let's go.
One versus one, so something else. You know, he probably did. Here's sorry, it's like, I can just imagine if I think on something, he's really quick and boom. And then they're probably.
Hey, watch our exam, right?
I was expecting. You just have the easy thing. I respect things.
Well, it's kind of like, ours, just really difficult to, so inevitably they may have four buildings.
I said for me. So take you all the way.
Most likely.
I didn't do it. So then he has a big.
But like, waiting for years to go.
Excuse me, are all the ANSYS, are they on the desktops already?
It should be, yeah.
Okay.
Whether they work or not will be an adventure, but I did test it on this one.
Okay, yeah.
Tested on one back there too, but hopefully they work on.
Okay, cause I'm just having trouble finding it in general, but if it's on.
It's, so you're searching for a program called workbench hacks.
Oh, is that what it is?
Yeah.
Okay.
We'll talk about when the activity starts.
Okay.
I think. No, it hasn't.
Yeah, I got me at least 3/4,
They
so
played a lot.
that should be golden,
You
thank
need
you.
more, like I keep everything charged,
Right.
figure,
So.
might as well come here and charge instead of,
Right.
so.
I got. To the.
Mine as well.
Because I studied for it, and I was like, I don't wanna.
Yeah.
And you'll probably let me know. But then I was running lately, and they didn't take it.
Forget transition.
No, I see, bro, I was like, bro. Like, I felt pretty. Like,
Even
the work
just
takes
based on
serious,
experience,
yeah.
I'm not it.
That's weird, bro.
But I also did.
Yeah, it is, as it was that time.
But it's a lot of them just spend relegation value.
What does that have? This.
Yeah, it's like stuff like.
It's like Jordan Henderson.
Plus, that was one right.
That one's crazy.
Oh, that was.
Not like I saw it, like it was.
Downloaded.
Yeah.
I'm just saying, go with first round manager, then get right. Remember when Brazil did that in
Say.
her vibes and they got eliminated in like the. Yeah. No, he got the.
Yeah, it's not too.
His wife goes down. Bro, it was crazy. She divorced him, so all his money bill and covering her.
Weird.
That's crazy.
That's insane.
Yeah.
I don't know. I think he should be in jail. I mean, obviously he did it. I don't think he's allowed to work there. We can't like ever go back to like personal or but.
Yeah. Crack stuff.
Yeah, what are we at?
I think that female batch, yeah, that's how I look at one of the circles, so.
Yeah, he's just like a move
other softwares and you, that's all.
Second.
It's like, why we're getting that grade. I think that's a problem.
He's like the Sean Blunt.
See if you can get that. That's like 10.
He used to be the quarterback. He got 28 elevation. And then he's currently the quarterback.
So broke.
Yeah. Because the Browns signed him. That's not as much Browns ever. Go back to my friend, he was saying, he Cleveland, so that's what it's That's what was better. No, I think it's Indiana. Indiana has to be. Tired.
What's it like that?
Both the Cleveland, like, both the little
Oh, shoot, right now, like 42%. It's not bad.
Well, here's we're going to just extract and go from the end.
Yeah, I guess extraction did so long.
They're going to hand it in again. They sound like, now it sounds like a high school football team, where they have. But they're probably gonna call them in again.
Yeah. Like numbers. Part of that topic is. Yeah. They're like, who's the numbers? Send it back, lead right here. Just send it and they just, I mean,
I mean, the Rams wasn't playing that, that's fine. We're in the Raiders play this. I don't know, like, the
Giants are going to do the resident.
the Giants and the Jets played. The only like actual New York team is. Basically.
Yeah.
I think the Rams are going all. They're two. They got Miles Garrett. He's like currently the best defensive player who's back in three.
Oh, it's not something.
So.
They basically got him for nothing. Or they got him, they got him for, I think, no, it wasn't the thing with Jared. Oh, I need.
I got it.
We're close. We're close.
Also, you have participation. I was just saying. Yeah, you get 2 points, bro. That's 1%. I'm also gonna get 1%. Yeah. Well, actually, surprised with it.
Well, I left like an entire section with them. I like, it was the one about. Yeah, I didn't. But I kind of wish I could.
Yeah.
Six, what is it called? Also, six.
Yeah.
I just couldn't remember what it was called, not the room 610. I was like,
All right, it's 25. Let's go ahead and get started. All right, so we are going to be doing our first ANSYS activity. And so if you go to the Canvas site, you'll see that there is a posted kind of instructions here. So if you go under assignments and you go under ANSYS activity 1, the specifications or instructions are here. So these activities, I've kind of designed them in a way where, you know, all the steps that you need to do for the activity are written out in the PDF. So I know some of you have already gotten started on that, so that's great. But what I'm going to do in the class during these activities is I'll go ahead and walk through everything that's in the PDF. We'll go and do that together, and then usually that takes about, it doesn't take the whole session. It takes, it's like 30, 40, 50 minutes. Today might be a little bit longer because it's our first time using the ANSYS. And then you're free to use the rest of the session to work on the rest of the activity. Because if you scroll all the way to the end, which is a lot, I know this is 19 pages, but there are additional activities and additional questions for you to answer as well. Okay. So we'll get all the way up until, until those extra problems there. So my goal is that for everyone to kind of finish their first ANSYS simulation today. Okay. Okay, so our first activity is kind of just the first activity that it's almost traditional at this point. A lot of online ANSYS workshops and ANSYS certification programs are going to have the same one, is the plate with the hole. Right? And so we're going to be simulating, we're going to be doing a 2D simulation of a two-dimensional plate that has a hole in the middle, and we're going to be subjecting it to a tensile pressure force. Okay, and so the plate is going to stretch out in tension. There's going to be some stresses that develop, just like we talked about before, and we'll see how it's going. So the main objective of this activity. So this problem is not particularly complex at all. The main objective of this activity here is to just be everyone's first exposure to ANSYS, get used to where all the buttons are, and basically how to apply all the things we've talked about so far in terms of meshing, boundary conditions. Okay. Okay, so to start, let's do this before I talk anymore. Let's go ahead and launch ANSYS, which is not as straightforward as you would think. So if you've installed ANSYS on your personal computers, or let's say you're in the lab here and you're working on computers here, to launch ANSYS, we actually need to launch a program called Workbench. And so if you open up your start menu and you search for Workbench, okay. If you're using the version in the lab, it should be 2025 R2, which is the revised version of the 2025 ANSYS. I think I saw yesterday, if you downloaded the version on your home computers, it should be 2026 R1. So it doesn't really matter, we're mostly just going to be using just the basic features in ANSYS, so there's not that much difference in between the two. You may have some issues if you're trying to kind of work in between the two. So you can upscale your ANSYS files from an older version to a new version, but you can't go the other way. So if you start a project or you work on a project on your own personal computer, it's actually very difficult to import that back into an older version of ANSYS. So just kind of be aware of that. Okay. All right. So let's open up Workbench. Okay. It does take some time, and so it's ANSYS is not a light program at all, which is kind of one of the criticisms that it gets. But if you're used to SolidWorks, it's definitely not as, it's probably about the same heaviness as SolidWorks, and so it does take a while to achieve. Okay, so while that's going, I'm going to go ahead and talk through the rest of the setup here. Okay, so like we talked about yesterday, when you're running a finite element simulation, you're primarily concerned with the problem set. Okay, so we're going to set up the problem, we're going to set the mesh, the boundary conditions, the material properties, and then we're going to let ANSYS solve it for us. Okay. So whenever you are running a finite element simulation, it's always important to be aware of its underlying boundary value problem, like we talked about yesterday. Okay. So this is the boundary value problem specifications for our project here. So we have our plate. This is our geometry, our domain. Okay. So we have a rectangular plate with this circular hole in the middle. The dimensions of the plate are given by this table down here. So it has a length of 300 millimeters, a width of 200 millimeters. The thickness or the thickness of the plate that goes within the page is 5 millimeters. So even though this is a two-dimensional simulation, we do need to specify its thickness. Okay. The hole diameter, which I realize is not to scale, is 50 millimeters here. Okay. The load that we're going to be applying here is 1,000 megapascal. Right. So that's a pressure. The Young's modulus is going to be 2 times 10 to the 5th megapascal, and the Poisson's ratio, which is another material property, is 0.40. Okay, so as you're going to see, as we kind of go through the activity, we're going to be specifying all of these by defining the geometry and the material properties. Okay. Okay. So hopefully everyone has launched Workbench. So is everyone able to kind of get the screen here for ANSYS? Okay. Good. And I'll be pausing throughout the activity today. I'll make my rounds, and then I'll if you're having trouble, just raise your hand. Okay. Okay, so this is kind of the starting point for every ANSYS simulation. This is our Workbench. So first thing I want to draw your attention to is all the different analysis systems here on the left-hand side of the screen. Okay, so remember we talked yesterday that we said that ANSYS or finite elements in general is just a method for solving different types of physics or governing equations. And so you get a little bit of a preview here in terms of all the different types of physics that ANSYS can solve, right? So the one that we're going to be using a lot in this class is this one right here called static structural, okay? Which is solves a structural dynamic simulations in a static situation, okay? But you can see here, there's also options for thermal, right? So you have transient thermal, steady state thermal. We have our fluid simulations here. We have actually 3 different types of fluid solvers, which is interesting. Here we have electrical, so that is your electromagnetic type simulations. We can even do vibration analysis. We can solve for the harmonic modes as well. Okay. So we're going to spend most of our time here, but then we'll go over some of the more other features later. Okay. So to start a static structural simulation, we're going to click on static structural, okay, and we're going to drag it into the workspace here. And so when you click and hold static structural, you will see that there's going to be a box that shows up in the workspace here. So you can click and drag it there. Another way you can do it is you can just double click on static structural and that'll create the object here as well. Okay. Okay, so whether you click and drag or double click, you should see this new window that shows up for static structural. Okay. All right. So first thing we're actually going to do is we're going to confirm our material properties because that's the first thing that shows up on this list. Okay. Now, the nice thing about ANSYS is that it kind of shows you it kind of almost lays it out for you in terms of all the steps you need to run or complete in order to run your simulation. So first step here is your engineering data. So we'll review that in a second. Next is your geometry. Next is your modeling, which is going to be your mesh. The setup, that's going to be where we apply the boundary conditions. Solution, that's when we actually solve this, and this is the results. Okay. So we're basically going to be going down this list here one by one and setting all the different settings that we need to run the simulation. Okay. Okay, but first thing we're going to check here, let's go ahead and check our engineering data first, because this is where we're going to check our material properties. So go ahead and double click on engineering data. Okay. And you can see here, after you double click on that, you can see the list of materials that we have loaded for our particular simulation. Okay. So the way ANSYS works is that if you have a different material that you want to use, you need to load it into your project. Okay. But by default, ANSYS has one material that it always loads in, which is structural steel. Okay. So if you want to check the properties of structural steel, you can go ahead and left click on that. Okay. And then you come down here. This data table down here will show you all the different material properties for structural steel. Okay. Okay, so first thing we're going to check here is we're going to check if our material properties match what we need for this particular simulation. So the 2 material properties that we're given here are the Young's modulus. Okay. So the Young's modulus is 2 times 10 to the 5th megapascal. So let's go ahead and check that first. So let's go back to our workbench here. Okay. So let's search up the Young's modulus, which should be under this setting here, isotropic elasticity. Okay. Okay, so if we expand this menu here for isotropic elasticity, you can see here that we have an entry for the Young's modulus. Okay. So the Young's modulus is given to us right now as 2 times 10 to the 11th Pascal. Let's go ahead and change the units for this just to make it consistent with our document. So to change the units, oops, we can go ahead and click on this drop-down menu here. Click on megapascal, right? And you can see here that our Young's modulus is indeed 2 times 10 to the 5th megapascal. So our Young's modulus is good. Okay. Next thing we're going to check here is the Poisson's ratio. Which we can see here is 0.3, okay, which matches exactly with what we have here, right? So our material properties in this case are good. So there's nothing that we need to change, just because I've designed this activity to work with structural steel. Okay. Starting in the next activity, we are going to be adding our own material properties, but for now we're just going to leave them as structural steel, just because that's what we're using for this activity here. Okay. All right. Any questions on the material properties?
So we just change our Young's modulus if it wasn't the same.
We're not changing anything, and so the Young's modulus was already in the right, already correct. The only thing we changed here was the units in which we're displaying. So by default, it displayed it as Pascal. And so just because our document here shows our Young's modulus as megapascal, and so we just changed the unit here just to be consistent. But also, if you're a bit savvy, you know that a megapascal is 10 to the 6th of Pascal. And so, you know that 2 times 10 to the 11th Pascal is 2 times 10 to the 5th megapascal. Yeah. Okay. All right. So we don't need to change anything here. So let's go ahead and close it. So go ahead and click the X here on this tab on the top for A2 engineering data. Okay. So that's going to take us back to our workbench. Okay, so the next step we need to do here is we need to define our geometry. But before we do that, we need to do one special step, which is just for this activity, because this is the only activity that we're going to do in this class that's going to be 2 dimensions. Okay. Every other activity we're going to work in 3 dimensions, but we do need to specify that. So to specify that our simulation is going to be in 2D, you're going to right-click on geometry. And then you're going to click on properties, okay? And so that's going to let you edit the properties or the macro properties of the geometry before we start defining. So go ahead and click on that. And then after you open up the properties, you're going to go to line 19 here, where we're going to define the analysis type, okay? So you can see by default, the analysis type is 3 dimensions, just because, for the most part, it's, finite elements is a 3-dimensional technique. But only for this activity, we need to change this to 2 dimensions here. So make sure you change it to 2D. If you don't change it to 2D, it is going to cause some issues later. Not that it's that big an issue. This activity is actually very short. It's going to seem very long just because I'm talking through everything. But if you start it from scratch, it actually only takes about 5 minutes. And so, if you forget to do this, or you get later on and it's still 3D, you just need to make sure you change it there. But for now, let's go ahead and change this to 2 dimensions. Okay. Okay. So make sure your analysis type says 2D there. All right. And then once you are done with that, we are ready to make the geometry. So, once again, make sure that your analysis type is 2D, and then you're going to right-click on geometry, and then you're going to click the second option here for new design modeler geometry. Okay.
Just a heads up, Professor. Anybody that's got the newest version, it gives you 3 options. The top one is some other workspace it's like office space or something like that.
Okay. Yeah. So one thing that ANSYS has been adding has been different CAD programs. So Design Modeler was kind of their original one. I know they've added Discovery recently, and probably the third one's called Space Claim or something like that.
That's exactly what it is.
Yeah. So we'll use Space Claim for activity 4. I haven't actually used Discovery yet. That's something that they just made within the last year or so. So I do need to experiment with that. But for this activity, we'll use Design Modeler. Okay, so go ahead and click on New Design Modeler Geometry, and that's going to open up a new program. So the way that ANSYS works, so ANSYS is actually not just one program. It's actually a bunch of different programs that are kind of just all duct taped together. So Workbench is kind of the manager program, so that's kind of where everything is launched from. But from Workbench, you're going to launch into different programs that do different tasks within the finite element process. Okay. So Design Modeler is one program that we're going to use to make the geometry. Okay, so is everyone able to launch Design Modeler and have this window open here? Okay. Question? Yes.
Yeah. So I think I was just lagging a little bit. It's just loading, but did you just double click on geometry, or did you right click on that to get that kind of table that sort of stuff into 2D?
Yeah. So you have to right click on geometry and then hit properties. And then you should be able to change the analysis type there from 3D to 2D. And then once you do that, you can right click on geometry and then you want to edit the geometry in Design Modeler. Yeah, so all this is as well is in the PDF. I am going to, I do want to make sure I get to the end before the end of class today. And so, if you're having issues, just, I'll come around a bit later. But all this is in the PDF as well. So if you fall behind, you can look up in the PDF. Okay, so let's go ahead and go into Design Modeler here. Okay, so for this activity, this is going to be the only activity that we do this, just because, for the most part, we're going to be importing our own geometry. But for this activity here, we're actually going to draw it out just because it is so simple. Okay, so first thing we're going to do is we're going to look at the XY plane, and we're basically going to make a sketch in that plane. Okay, so go ahead and left click on XY plane here. Okay, and then if you want to change the view so that we're looking just straight on the XY plane, you can go ahead and left click on this Z axis down here. Okay, so by clicking on this blue Z arrow, we're going to change our perspective so that we're just looking straight down on the XY. It's just going to make it a little bit easier for us to sketch our rectangle. Okay. All right. So let's go ahead and jump right into it. And so to start sketching, let me move this over to this side here. Okay. Make sure that you have XY plane left click here. And then we're going to click on the sketching tab here. So that's going to allow us to bring up a new menu where we can actually start to draw out different shapes. Okay. Okay. So if you're familiar with SolidWorks, you know, probably this should be kind of second nature to you. Design Modeler is not meant to be a main CAD program, so just kind of keep that in mind. It's not as fully featured as SolidWorks, but the basics are here in order for us to get what we need done. Okay. Okay. So we need to draw a rectangle here, right? So the rectangle was kind of the base of our geometry. But before we do that, we need to make sure that our unit system is consistent to what we need, okay? Because if you look at the bottom here, right, you can see right now that everything is being measured in meters, right? And so the distance from, you know, this point to this point is 30 meters, okay? Which is way too big for what we need. Because if you look at the, our project document here, you can see that the total length of our plate here is only 300 millimeters, which is only 0.3 meters. Okay. So first thing we're going to do is we're going to change the unit system so that, you know, it makes it a little bit easier for us to draw. Okay. So to change the unit system, you're going to go to the top left of the screen. And so there is an option here for units. So go ahead and click on that. And you can change the unit system to any of your SI units or English units here as well. So for us, let's go ahead and change it to millimeter. Okay. Okay, so make sure you are on millimeter here. And then once you do that, you can see in the bottom of the screen, our ruler has changed as well. So instead of being measured in meters, we're now in millimeters, which is going to be more convenient when we start to add dimensions to our geometry. Okay. All right, so let's go ahead and draw a rectangle. So let's go ahead and left click on rectangle here. Okay. So that's going to activate a pencil here on the main screen. So to draw a rectangle, it's basically a 2-point drawing. So you're going to click once to establish one corner of the rectangle. Okay. Right, and then you're going to click and drag, and then you're going to drag that other the other point to define the other point of the rectangle. Don't worry about the length. We are going to dimension that in a second. The only thing you need to make sure is that you just define the overall shape of the rectangle. Okay, so is everyone able to get the rectangle drawn in the plane here? Okay, good. Okay, so let's add dimensions. So let's go ahead and set the length and width of this rectangle. Okay. So to add dimensions or to define the length of the rectangle, we're going to go to this tab here for dimensions. So let's go ahead and left click on that. Okay. And by default, it's gonna allow us to choose what's called a general dimension. Okay. So to add a general dimension, we're going to left click on one of the sides of the rectangle. Okay. So let's start with one of the horizontal edges. So you can either pick the top edge or the bottom edge. Okay. So let's go ahead and left click on that. And then let's bring out this dimension here and then left click again to establish that dimension. Okay. Now, dimensioning in ANSYS is a little bit different compared to SolidWorks. I think probably what you're accustomed to is, you know, there's a window that pops up here where you can set what you want the length to be. Okay. Instead, what you have here is you have a variable. So it's a little bit hard to see on the screen, but that says H1. It should also say H1 on your screens as well. So to actually specify that length, you're actually going to go to the bottom left-hand side of the screen. Okay. And then set the value for H1 in this menu down here. Okay. So this is a convention that ANSYS uses a lot. So generally, the bottom left-hand side of the screen is used for any kind of settings that you need to establish for the simulation. Okay, so you're going to see we're going to specify things like the mesh size, the mesh shape, the mesh order. Usually, it's in the bottom left. Okay, so bottom left is usually reserved for any kind of settings that you need to apply in ANSYS. Okay, so let's go ahead and set this value to be to match our specifications here. So the length of our plate here was 300 millimeters. So let's go ahead and set that length H1 to 300. Okay. So just click it, type 300, hit enter. Okay. You can see that makes the length of that rectangle much larger there. And so let's do the same thing, but let's now establish a dimension for the width. Okay, so go ahead and click on the vertical edge of the rectangle. Go ahead and click it out. Right, and then let's come back to the bottom left-hand side of the screen and set the value for that width, which we know from our specifications is 200 millimeters. Okay. And you can scroll on the mouse wheel to kind of zoom out as well. Okay, so now we have our rectangle here. Okay. And we need to move. Okay. Oh, by the way, if you want to pan, right? So probably you're having this issue where you're kind of zoomed in like this and you can't see the whole rectangle, right? You can scroll on your mouse wheel to zoom out, but if you want to pan or move the entire thing, you need to hold Control on your keyboard and then hold the middle click, hold the mouse wheel. And then by doing that, you can kind of move the image around. So this mouse is a little scuffed, and so I can't really move it all too much. Oops. But that's how you move it around to get it different. Okay. All right. So now that our rectangle has the proper dimensions, next thing we're going to do is we need to center it. Okay, because eventually we're going to put a hole in the center of this rectangle. That'll be a little bit easier to do if the center of the rectangle is aligned with the origin. Okay. All right. So let's go ahead and add another dimension. So let's go ahead and change our dimensioning type. So instead of the general dimension, we're going to set a horizontal dimension instead. So what the horizontal dimension is going to do is that it's going to allow us to set the horizontal distance between any two lines in our geometry here. Okay. So in particular, we want to set the horizontal distance between this vertical edge here and the y-axis. Right. So to set a horizontal dimension, you need to click on both. Click on both edges there, and it's going to allow you to specify the dimension in between them. Okay, so that's going to be H3. So let's set H3 to be half of the length in order to center this rectangle on the y-axis. Let's set H3 to be 150. Okay. You can see now that our rectangle is moved to the left. And then let's do the same thing with the vertical dimension. So we're going to left click on vertical dimension from this menu here. Left click on the x-axis, left click on a vertical part of our rectangle. Okay, that specifies a new dimension of V4. And so let's set V4 to be 100. Okay, so now our rectangle here is fully centered on our board. It has a proper length, it has a proper width, and then we've centered it so that the center of the rectangle coincides. One thing you'll notice too is that once our sketch here is fully defined, and so all these lines are fully fixed in space, they turn this kind of like dark blue color. And so that's kind of a good indication of making sure that your sketch is fully dimensioned, fully defined. Which is typically a good practice to do, probably as you've learned from songs. Okay, any questions on this so far? Yes.
Oh, where did you say the dimensions were for the vertical and horizontal?
Yeah, so we want them to be half of the length and half of the width. And so this the horizontal distance between this edge and the y-axis, that's going to be 150. And then the vertical distance between the x-axis and the bottom of the rectangle, that's going to be 100. Yeah. Okay, good. All right, so next thing we're going to do is we're going to draw our hole. Okay, so our hole is just going to be a simple circular hole right at the origin. Okay. All right, so let's go ahead and click draw. Let's go ahead and click on, so let's go ahead and return to the sketching menu. So click on draw, and then you want to click on circle here. Okay, so go ahead and click on circle, come to the origin here, left click on that. Okay. Now we can click and drag out. We can specify the size of the circle. Okay. So once again, it doesn't really matter how big you make it. We're going to dimension it in a second anyway. So go ahead and click and drag. I'm just going to make it this big here. Okay. Right, so now we've drawn our hole. The next thing we need to do is we need to dimension it. So just like we did with the rectangle, we're going to left click on dimensions here. Okay. We can click general dimension just because diameter of the circle is a general dimension. We can click anywhere on the edge of the circle, click on that. It's going to allow us to establish this diameter here, okay, D5. And then we're going to set D5 to be the diameter, which is 50 millimeters. Okay, so now our plate here has all the proper dimensions for our simulation here. Okay, we defined the geometry. The only thing we have to add now is just the thickness for this plate. Okay, good. Any questions on this so far? Okay, good. All right, so now that our sketch is done, next thing we need to do is we need to add thickness, right? So usually if you're in SolidWorks at this point, you would do an extrude operation, but remember, we are doing just a two-dimensional simulation. So we are going to add thickness, but it's going to be kind of more like a phantom thickness that's mostly just used for the simulation, okay? So to return back out of the sketching window here, you're going to left click on this tab for modeling. Okay. So let's go ahead and left click on modeling there. And returning back to this menu here, we can see if you left click on XY plane, you're going to see we have a new sketch here called sketch 1. Okay. Okay. So basically, we need to turn this sketch into a surface in order for us to run our simulation on. Okay. So to do that, right, make sure sketch 1 here is highlighted. Go to tools, or excuse me, go to concept. Okay. So concept is a menu from the top of the screen there. And what we want to do is we want to add something called surfaces from sketches. Okay, so which should be the third to last option from that menu down there. All right, so go ahead and left click on that. That creates this surface sketch here, okay? Okay. So to do this, we need to apply this to a certain base object. And so you're gonna go ahead and left click on sketch 1, okay? Because that is the object that we want to apply this to. And then with sketch 1 highlighted, you're gonna click on apply right here, okay? Right, and so if you did that correctly, you should see when you're setting the settings for the surface sketch 1, you should see that the base object should have just one sketch, which is referring to the sketch that we just drew here. Okay. Okay. All right, so we can go ahead and do that, and then we need to set the thickness, which is basically the amount that we're kind of extruding out into the z-axis. Okay. So if we return back to our project specifications here, we can see that the thickness is 5 millimeters. Okay, so let's go ahead and specify that. So we want a thickness of just 5 millimeters here. Okay. All right, so with that all settled there, in order to generate our surface, we need to hit this lightning bolt option up here for generate. Okay. Right, so make sure that everything is good. Your sketch is all dimensioned properly. Your surface sketch is set properly with the right thickness and referring to the right sketch. Okay, so go ahead and click generate. And if all goes well, you should have your geometry that looks just like this. So you should have a solid plate here, and there should be a hole where the hole is meant to be. All right, everyone able to get this in their design modeler so far? Okay, good. All right, great. So that's good. So now our geometry is established. And so now we are ready to mesh the geometry here. Okay. So the meshing is actually taken care of in another program. And so, one annoying thing with ANSYS is that, sometimes you have to close programs and open different ones in order to continue. Okay. So you want to be careful here. So we want to close out of Design Modeler. Okay. But we don't want to close Workbench, right? So Workbench, remember, that's our manager software. The only thing we want to close here is just the design model. Okay, so go ahead and close that. Don't worry, it's saved automatically. So if you close Design Modeler, okay, you should be able to return back to Workbench. But one thing you should notice is that our geometry now should have this green check mark. Okay. So what that's telling you is that the geometry is set properly within ANSYS, and we're now ready to move on to the next step. Okay. Okay. So the next step is to open up another program called ANSYS Mechanical. And so in order to do that, we're going to double click on the step 4 model here. Okay, so you double click on this. It's going to open up another program called ANSYS Mechanical, where we're going to run the rest of the analysis for today. So thankfully, we're going to spend the rest of the time in Mechanical. Mechanical is the program we're going to spend the most time in, because that's where we apply the boundary conditions, the mesh, and we view the simulations. Okay, but because of that, Mechanical is a bit of a heavy program, so I'm going to let it run. I'm going to take 5 minutes now to kind of just walk around just briefly. If you want to continue so the next step is the meshing, and so if you're following along in the PDF, that is page 9. But I do want to kind of walk around a bit just to make sure everyone has set the geometry appropriately. Okay. If you're launching Mechanical for the first time, you can choose the theming. Okay. All my friends think I'm a psycho because I prefer light mode. But if you want to save your eyeballs, I guess you can pick dark mode, but I actually prefer the light. Or you can go with the classic. Classic is that's kind of what I've always known as well. So, but you can choose. It doesn't really matter. Just whatever you kind of most prefer. Okay, but I'm gonna go ahead and make my rounds, and I'll come back at around 5:01. If you're having issues, just raise your hand. I'll come. To 5 millimeters for thickness. You said it there, so that's so you want to change your units here. So the units go here. Yeah, so you probably want to do it back in the sketch. So go ahead and delete this for now. So I'll click on search sketch. Go back to Okay, let's make sure your sketch is in the right units. Go ahead and click on the sketch there. Yeah, so right now your play is waiting for yeah. That's good. Are you guys doing good?
It's good. Nice.
Are you guys doing? Okay. Okay, so yeah, your men look good. You can on your pole. Yeah. Okay. So you can zoom in. So there's zoom all the way.
When I first made it, like the first dimension was really small.
Yeah. Yeah, so you want to go back to the circle. Yeah, go to the origin, there you go. There you go. And then you can dimension that to be 50. Yeah. Good. Well, go ahead and split one. Let's put one that is one. So I'm going to update with it. Right, looking up again for the tree. Are you
No, you're not supposed to be involved. No.
Oh, sorry. Let's go ahead and close this. Yeah. Let me come back and see. I mean, we got how it is. You guys come back here. Okay. Good. Good.
I just set it up. Yeah, it was.
Okay, so that's the other CAD software in Full Discovery. So you want to open up and design models. So go ahead and close that. Yeah, go ahead and right click on John. I think it's coming up just right with one. Yeah, so when you right click it, there's a menu that on new design. may want to try your house that way. Yeah, good. And then new design model. Should be good. Yeah. Chris, Snow, you something? Andrew, good? Bye. Everyone on Zoom, you guys are following along okay? Thanks, Simon says yeah, okay. How can you change the dark? That's actually a good question. So the light mode and dark mode is actually something new. I actually don't know how to change it afterward. I'm guessing it's part of display. You might be able to change it here. You can also search, and so ANSYS actually has a pretty good search feature. So after you launch mechanical, you can click on this and search maybe dark mode. I'll have to look it up. I actually don't know how to change it after you set it with done. Any other questions from Zoom before we move on? Okay, so let's go ahead and move on. So if this is your first time opening up mechanical, you might be greeted by this screen. So it's going to ask you to like and subscribe to their YouTube channel, which we're not going to do. But if you want to view your geometry, you can click anything here on this left panel. But if you left click on geometry here, you should be greeted with your plate with the hole, right? And so if your geometry attached properly, then you should be greeted with this. Although I know there's issues with that a little bit too, so I'll come back around for that. But let's go ahead and mesh this, okay? Okay, so the next step in the process is to generate a mesh for this geometry. So one thing you should notice from the outline here is that the mesh has this little yellow lightning bolt next to it. And so what that means is that you need to generate a mesh, okay? So let's go ahead and generate a naive mesh first. So let's go ahead and right click on mesh here, okay? And then you can left click on generate mesh, okay? So that's going to generate a mesh just with the default setting. So we're not specifying anything for the size, the shape, or the order, right? And so we can kind of see just what ANSYS just makes automatically, okay? Now, when you ask ANSYS to make a mesh like this, it's not trying to do it based on accuracy. It's just trying to get you a mesh that's going to work in the least amount of time possible, okay? So you can see here we have a mesh, right? And so this is our first mesh that we're actually looking at for our practical case here. Okay. So you can see here that we've taken our geometry, which is a plate with a hole, and we've broken it up into these elements here, right? And you can actually see, so this mesh is actually very interesting. So there's going to be, so you see there's a mixture of rectangular elements here, okay? So you can see here we have quadrilaterals, but we also have a few triangles as well. So we have a triangle here, and triangles here, and a couple more triangles down here as well, okay? It's kind of a weird, funky looking triangle right here, okay? So this is not uncommon, right? And so a lot of times, even when you specify for a mesh to be a quadrilateral type mesh, sometimes it's impossible for the entire mesh to be all quadrilaterals. And so ANSYS may have to put in a few triangles there just to make the geometry work. But for the most part, ANSYS will try to make your mesh as as quadrilateral as possible. Okay. Now this mesh will work, and so we can run a simulation on this. But this is what I would probably characterize as not a great quality mesh, because this is very poor. Okay. In fact, you can actually check to see how many elements are in your mesh. And so if you go down to the bottom left-hand side of the screen, there is a tab here called statistics. Okay, so make sure you've left click on mesh here. Okay. So if we check the statistics for this mesh, you can see here that we only have 75 elements in this mesh, which is a very, very small amount of elements. And so the amount of elements that you need for a given simulation is obviously very kind of problem dependent. So there's no kind of magic number that you need to aim for. But no matter the circumstance, 75 is a very small amount of elements. Okay. So first thing we're going to want to do is we definitely want to refine this mesh. Okay. So to refine this mesh, to basically make the elements smaller, we're going to right click on mesh here. Okay. And then after you right click, you're going to go to insert. And so this is basically the way, these are all the different types of mesh settings that you can apply to your mesh, okay? Now, we're only gonna add a small portion of this. We're not gonna use a lot of these because a lot of these are very kind of niche, right? So you can add a welding here to create kind of a specific joint. There's mesh inflation, which is used for fluids, okay? But some of the most basic settings are what we're gonna use up here, okay? So the first thing we're gonna add here is a sizing object, okay? So let's go ahead and click sizing, okay? So this is going to allow us to change the size of our mesh, okay? Okay, so after we create our mesh sizing object, we're gonna look in the bottom left-hand side of the screen. You can see there's gonna be two settings that we need to specify. One is gonna be the geometry, which is gonna be the portion of our model or portion of our geometry that we want to apply the size to, okay? And then we can specify the element size as well, okay? All right, so first let's go ahead and specify the geometry. And so for this, there's only one aspect of the geometry, which is just our plate. And so there's not much to choose here. So go ahead and left click on the plate. You're gonna see the entire plate is gonna highlight green, okay? You're gonna go to geometry here where it says no selection. You're gonna left click on no selection and then hit apply, okay? And so you're gonna see that your geometry is now gonna be applied to one face, which is our plate here, okay? Okay, now we need to specify the element size. I apologize. So let's do this as well, just to make this a little bit less obnoxious. So right now, the default units for this ANSYS mechanical are in meters. So you can keep that if you want, but if you want to make things a bit more convenient, you can click on home on the top of the screen here. And then if you go to the middle of the screen, you're going to see that there is a button for the units. So just like we did in design model, where we can change the units. So let's go ahead and change the units to millimeter. Okay, so that's going to be millimeters, kilogram, Newton seconds. Okay, so then now that's a little bit easier for us to kind of specify for our mesh size. So we can see our mesh size, the default is 30 millimeters, which is pretty big for this plate. Okay, so let's go ahead and make this smaller. So let's go ahead and make it just a little bit smaller. Let's start by cutting it in half. So let's make our mesh size 15 millimeters. Okay. So go ahead and set that to 15. And let's regenerate our mesh. And so to regenerate the mesh, you're going to right click on mesh, just like we generated the first time, and click on generate. Right. So it should be pretty fast just because this is a pretty simple geometry. And you can see we have a vast improvement for our mesh already. Okay. So you can see here our elements are much more higher quality, right? So everything is much closer to its ideal quadrilateral or equilateral shape. Okay. We still have a few triangles, which is not that uncommon, but for overall, this is a much better mesh shape. Okay. And so in fact, you can kind of play around with this a bit more. So you can see, let's look at what a 10 millimeter mesh looks like. Keyboard will listen to me. Good. Keyboard lose connection. Keyboard might have lost connection. So weird. Okay. Anyway.
That's why. That's terrible. That's terrible.
That's so strange. It quit right in the middle of the lecture. Oh, the volume button works. Hang on. Let me try minimizing this. This activity was going too smooth, so the keyboard was like, "We're going to have none of that. We need some drama today." Okay. Anyway, so you guys can play around with it. Unfortunately, it seems like my keyboard is kind of tripping up right now. I'm not going to investigate this in a second. But you can play around with the different sizes as well. Okay. For this activity, it doesn't matter too much, and so this case is so simple. You should be able to get an accurate solution. With anything lower than the default mesh size. So even with 15 millimeters, it should work. But definitely play around with it and kind of see what changes from there. Okay. So the next thing that we're going to add here is we're going to add a method object. Okay. So the method object is going to allow us to change the shape of the elements as well as the order. Okay. So once again, let's go ahead and right click on mesh. We're going to hit insert, and then we're going to go to method. Okay. And so the method object is something that allows us to specify shape and order. Okay. Okay. So let's go ahead and create that. Right. Once again, we need to specify the portion of the geometry. So let's go ahead and left click on our plate here. and hit apply. Okay. All right, so now we can go ahead and set the settings here, right? And so you can see here that we can set the order and we can set the method here as well. Okay. So the method, that's going to be our shape, right? So if we actually left click on this setting here, right? So you can change the shape to either be quadrilateral, dominant, or triangles. Okay. So let's change it to triangles for a second and let's see what that looks like. And then for the order, right? Remember, for order, we have the option of either a linear element or quadratic element. Let's set quadratic just because, there's no reason not to. Right, so let's go ahead and see what our mesh looks like here with triangular element. Let's go ahead and generate the mesh. Okay, so you can see here that our mesh visually looks a lot different now. So all the elements are now triangles. But the mesh size is about the same. Okay, let me see if I can change this now. Okay, now I can change it. That was so weird. Okay, so let's see what it looks like with 10 millimeters. Okay, so all right, so you can see, as we change the mesh sizing, as we change the shapes, our mesh changes accordingly. Right. Now, for this activity, like I said, most of these changes are mostly just visual. They're not really going to change your output just because, again, this simulation is quite simple. But for more complicated cases, your mesh is going to make a big impact on yours. Okay. Any questions on this so far? Yes.
That's ANSYS mechanical, right?
Yes.
When we select on the model, is that a discovery firm?
No.
So a little bit. There's something else.
Okay. I'll come back. I'll come back in about 10 minutes and I'll help you guys out. Yeah. All right, any other questions on the mesh here? Okay. All right. So last thing we're going to do on the mesh, just like I kind of referenced earlier, one thing we're going to see from this simulation is that the stress is going to concentrate around the hole. Okay. Actually, let me do this first. So let's actually switch this back to quadrilateral. Triangular mesh is actually going to be part of one of the activities later. Okay. So we want to refine the mesh around the hole. So one way that we can do that is we can add a refinement object. So if we right click on mesh here, we can go ahead and hit insert. The third option under the mesh here is refinement, which allows us to specify, a region where we want to refine. Okay. So go ahead and click that. Right. And so this is going to allow us to refine the mesh around our hole. Okay. All right. So to do that, we need to select the hole here, right? But you want to be careful because we don't want to refine the mesh everywhere. We only want to refine the mesh around the hole. Okay. So to do that, we're going to make sure we can only select just this edge here. Okay. So if you look, so it's kind of a subtle kind of setting here. But if you kind of look near the middle top of the screen, you can see here that there are different modes of selection. Okay. So by default, we have this one selected, which is what's called a surface selector. Right, so when we mouse over things, the ANSYS is going to snap to whatever surface that we're selecting to. Okay, we don't want that, and so in order to select around the hole, we want to select this edge selector right here. Okay, so let's go ahead and left click on edge selector right here, right, and then let's go ahead and left click on the hole. Right, so around there you should see the outline of the hole outlined in green. Go ahead and hit apply. We'll go ahead and leave the refinement level to 1. We'll kind of discuss that a bit afterwards. But let's go ahead and regenerate our mesh and let's see what the mesh looks like with that refinement there. Okay, so with the refinement, you can see that we're back to quadrilaterals, but in the region around the hole, you can see that we have slightly smaller elements here. Okay, so that's going to help us, when we are generating our solution results, because that's where the stress is going to concentrate in our simulation. Okay, good. All right, so kind of right away, you kind of see the application of our discussion on the mesh. Okay, so we have mesh sizing, mesh shape, and mesh order. Okay, next thing we need to do is we need to specify our boundary conditions. So let's go back to our specifications here. Okay, there are 2 boundary conditions that we need to apply. So remember, boundary conditions are any kind of external effects that are going to be affecting your simulation results, okay? So on the left-hand side of our plate here, we're assuming that our plate is attached to a wall, okay? So for all intents and purposes, what that means that this side of the plate is going to be fixed. Okay. And then on the right-hand side, we are going to be applying a tensile force. But in fact, the tensile force is actually given in the units of pressure. Okay, so it's going to be a tensile pressure. Okay, so those are the two boundary conditions that we need to apply. So first is going to be a fixed support. Second is going to be a tensile pressure. Okay. All right, so just like we did with the mesh, we're going to specify those as separate objects in our ANSYS simulation here. Okay. So we're going to right click on static structural A5. So this is going to allow us to set boundary conditions. Okay. We're going to hit insert. First thing we're going to do is we're going to insert our fixed support. Okay. So you can see here that, these are all the types of boundary conditions that we can have. There are a lot of options here just because there's a lot of different types of boundary conditions out there in reality. But the one that we want for this particular job is a fixed support. Okay. So let's go ahead and left click on fixed support. Right. So now we need to specify the region of our geometry where we're going to apply fixed support boundary condition. Okay. Okay. So we want to specify the left-hand side of the plate to have that fixed support. So go ahead and left click on this edge right here. Okay. And just like we did with the hole, you should see that it should highlight green when you click it. Okay. Make sure only the left-hand side of the plate is highlighted green, right? Make sure nothing else is highlighted green. Okay. Go ahead and hit apply. Okay. So now that left-hand side there is fixed, right? So we basically fixed that part of the plate to a wall, so it's not going to move. The other portion here is we need to apply a tensile pressure on the other side. Okay. So once again, we're going to right-click on static structural A5. We're going to go to insert. We're going to go to our list of different boundary conditions here. Okay. And the type of boundary condition that we need to specify here is a pressure, which in this case, we're not using it as strictly a pressure. Pressure is typically compressive, but we're using it as essentially a distributed force. Okay. So go ahead and click on pressure. That's going to create a new object here called pressure. Okay. Once again, we need to specify the type of the portion of the geometry where we want to specify this pressure boundary condition. Okay. So let's go ahead and go to the right-hand side of the plate. Left click on that. Right. Once again, make sure that only the right-hand side of the plate is highlighted. Go ahead and hit apply. Okay. Right. But unlike the fixed support, we also need to specify the value and direction of this force as well. Okay. Okay. So if you go to the bottom left-hand side of the screen, you can see that the rest of the settings are applied here. Okay. Okay. So by default, a pressure is going to apply the pressure in a compressive sense. Right. And so it's going to apply the pressure towards the middle of the plate. But we don't want that. In this case, we want the pressure to act in a tensile capacity. Okay. So you can do that in a couple different ways. And so one way you can do that is you can specify the magnitude to have a negative magnitude. Okay. So you can set this to be -1000. Okay. And so that's going to create basically a vacuum pressure on the right-hand side, which is going to be a tensile. Okay. But in my opinion, I think the more straightforward way is instead to apply this in terms of its vector components. Okay. Okay, so to do that, we're going to change the define by. So we're going to change this this setting here, right? So by default, pressures are applied normal to a surface or normal to an edge. We're going to change this to components. To change this components, this allows you to individually specify the X and Y components of the force for this pressure here. Okay. Okay, so we switch to components. You can see here now our menu has changed. So now we can specify the X component of that pressure force, the Y component. In this case, we want the X component to be 1000 megapascal. Okay. Right, and in fact, you should see an arrow here, although it's being hidden by this thing for whatever reason. But you should see that the arrow should be pointing to the right. So this is now going to be a tensile pressure being applied to our plate. All right, any questions on that? All right, we're almost done. And so once I kind of finish this up, next 5 minutes, I'll start making my rounds to kind of help and catch people. Okay. So now that we've set our boundary conditions, last step here is just to run the simulation. Okay. But before we run the simulation, we need to specify which outputs or which contours that we want to view. Okay. So to do that, we're going to right click on solution A6. We're going to go to insert. Okay. And these are all the types of outputs that we can specify. Okay. So there's a lot of options here, and so by default, ANSYS doesn't show you everything. Otherwise, it would just be a little bit too overwhelming. Okay. But let's go ahead and specify the types of outputs that we want. So first thing we always want to do is we want to specify the total deformation. Okay. So that's going to tell you how much your plate is going to be, or how much your geometry is going to be deforming in terms of length units. Okay. So let's go ahead and click on total deformation. Okay. Next thing, let's go ahead and specify the equivalent von Mises stress. Okay, so remember yesterday we defined what the von Mises stress is. Von Mises stress is basically a scalar representation of the total stress state in your plate. Okay. And then let's also specify let's also view the equivalent von Mises strain as well. Okay, just because we talked about strain yesterday. All right, so right click solution A6, go to insert, go to strain. And we left click on equivalent von Mises strain. Okay, so you should have 3 outputs selected there. Okay. I think in the PDF it also asks for maximum principal stress, but I think let's just focus on equivalent stress for now. Okay. All right, and so with all those things specified, just double check, make sure you have your 2 boundary conditions. You're happy with your mesh, so your mesh looks good. You have all the outputs that you want. Last step to actually run the simulation is to click on this button here for solve. Okay, so it should be under the home tab. Go ahead and click on solve. So it should only take maybe about 10 seconds to do. Okay. Right, so you can check the status of your simulation. So there should be a progress bar in the bottom left. For some reason, it's taking a bit longer than usual. Okay. All right, so you'll know everything is done when everything has this, nice green check mark there. Okay. So if you left click on each of these results, you can kind of see what your results are going to look like. Okay. So first we have the total deformation. So this is going to tell you how much your plate is deforming in response to the boundary conditions. Right. So first thing we notice here is that the deformation on the left-hand side of the plate is 0. So you can see this is that this portion of the plate is this deep blue color. Okay. And if we look at the color legend here, that refers to 0 deformation. And the maximum deformation is on the right side, which is where we're pulling from, which has a magnitude of 1.6847 millimeters. Okay. Let's look at the equivalent stress. Okay. So just like we just predicted, the maximum stress is occurring around the hole. Right, so we have kind of on the top and bottom edges of the hole. The maximum stress there is about 3,300 megapascal. Okay. And we look at the strain visually looks identical because we are assuming that this is a linear material. So stress and strain are just scalar multiples of each other. Okay. But you can see the values of strain here as well. Okay. Okay, so that is our first ANSYS simulation. Question from the chat. Your values are slightly different than the ones being shown. So your values are going to be dependent on your mesh, right? So remember, the mesh kind of changes your solution a little bit. So if your values are not, exactly the same as this one, it could be that your mesh settings are a bit different. Usually it's not that big a deal. I would say as long as the first 3 or 4 sig figs are about the same, then probably did everything right. If it's different in like the 5th or 6th decimal, then that's usually nothing to stress about. Question, yes. For the deformation, I have a max deformation of 1.6847. Okay. Okay. All right. So I'm going to go ahead and start making my rounds. Oh, sorry. One more question from the chat. Your deformation 1.7. Yeah. So I would say that's very close. And so, if you want to get a bit closer, you can fiddle around with the mesh settings a little bit. This mesh, I would say, is still a bit coarse. And so I think I used 10 millimeters. And so, if you change this mesh size, so, we can kind of just kill it with elements here. So So let's see what this looks like for a mesh size of 2. So this might take a bit longer here, but you can kind of change the mesh size and kind of see how it was. As long as you're kind of in that ballpark and your contours are about the same as mine, then you're probably pretty close. Okay, so I'm going to start making my rounds just to make sure everyone's caught up. But if you have reached this point, you can go ahead and start working on the rest of the activity. Okay, so if you scroll down to the bottom of the PDF, you can see here that there are short answer questions. There are different things for you to try, so you can change the loading. Okay, you can see what happens when you change the loading to 5,000 megapascal. You can change the size of the hole. You can change the mesh size. You can try with triangular elements as well. Okay, and then there are short answer questions here at the bottom. Okay, and so you should be able to answer these short answer questions based on the lectures that we did yesterday and today. Okay, all right. Any final questions before I start making my remarks? Okay, all right, so that's all I had planned for today. And so, if you're still having issues, that's kind of crazy, actually. So if you're still having issues kind of getting to this point, go ahead and raise your hand. I'll come around. If not, you're free to work on the rest of the activity, or if you prefer to work from home, I'm not going to lecture anything else today, so you guys are free to go. And so if you guys are heading out, thank you guys for coming today. With the summer session, we're meeting again tomorrow, so I'll see you guys tomorrow. But yeah, hope you guys have a good rest of your day. A quick question for the chat. What is the purpose of thickness? The way I interpreted that is like the part being extended, but like we're setting up the yeah. So the thickness, that's actually a good question. So I forgot to mention that. So if you look on the side of our plate here, you can see there's no actual thickness. So this thing is actually thin as a paper. But we are technically solving the 3D equations for solid mechanics. And so the thickness actually kind of more enters as like a material problem. And so when you run a 2D simulation, there is kind of you can think of it like an effective stiffness, which is actually the product of the Young's modulus and the thickness that you specified in design model. And so that thickness does play a role. You'll see it later on when we get to activity 4, actually. But you can think of it as just kind of another material problem. Yeah, but it's not a thickness that you can actually use. Example, we choose an edge instead of a face. Yeah. So this activity is a bit strange because it's in 2D. So you have to kind of use your imagination a little bit that there is kind of a thickness there. That's why we apply that pressure on that edge. But in reality, in 3D, you can only apply pressure on a face. Yeah. I think once we get to activity 2, it'll be a bit more. Yeah. Okay.
Anyone else before we go?
We talk about it first, though. We're able to figure out your attachment things. What is it?
It wasn't better, but instead of thinking of
Oh, yeah, I mean, thank you. Got it.
But that updated.
Yeah.
Appreciate the change.
So this is chocolate.
Yeah, so whenever you update the mesh.
So they're going away, so don't get rid of them. Anyone else? Don't take it.
Okay, thank you.
Why not? Real sure.
So and then generate the mesh.
Absolutely. You can make them? We did, yes. So me and the family, we make them. I did a culinary school when I first got out of the military. They're really good.
But I found that to be a really yeah. All right, so you guys are having issues? Yeah.
Go thinking into that candy. It's good.
Okay.
Absolutely.
Yeah.
We do it before we're done.
Sounds great. That sounds great.
Okay. What design? Okay.
Oh, no, you want to say, yeah, I think we need.
Oh, we have to edit the line. You open it up. So.
And then.
Yeah, so once you start creating a part and then you have found that like add a program that becomes the goal. And so you pick the second up, you discuss it, but he was already started. Yeah, should be. Yeah. It looks like you got it open. So you're good to go. Why is this? Yeah, it looks like. Okay.
He got the jet mark.
Okay. Yeah, unfortunately, the programs take a while. With discovery. It's yeah.
Oh, your units.
Within open it up again. It's kind of the unfortunate thing. ANSYS is a bit cumbersome and it takes a while to launch the program. That's why it's not a lot of people don't. ANSYS is nice because it has it's like SolidWorks in that sense. So it's more user friendly, but it's also more it's a lot slower.
So,
Yeah, it's one close out.
another comment. Oh, yeah. Yeah, double check.
So
Okay.
it's still. That's one. Go ahead and start with it. Thank you. Okay. So right click on now it's. Let's, okay, go ahead and try, let's try this in the mechanical. I think that's started, probably, but I don't know if it was model. I don't think it was even mechanical. Maybe I'll turn this side. Okay, you can close discovery. I think discovery is it's a good product, then it's meant to kind of put everything in one step. So that might be where we go, stack there. So all my data red alert.
Awesome. It seems like this is the default for a credit. Yeah, that's why I opened up the second.
Gotcha.
Students, this is in this sentence.
It's like it's still attached, but that's still starting. Yeah, so even if the window opens, there might still be some, no check back and forth.
Oh, yeah.
Check this one. So it might be trying to have.
This very similar to ANSYS over here.
What is that? What is that?
I have a. It's some.
Oh, really? Okay. Okay.
I always see edits on like job types. Abacus and master.
I heard Abacus. I've used Abacus. Abacus has been more respected in the sort of community that it has. That's kind of its background. Started as a research software. ANSYS has always been a competitive software, and so people in the academic community might get that much. I honestly don't use the ANSYS or anything about it, but I know that industry like sort of, but there might be but there might be other programs. Like ANSYS is the first I've heard of it. There might be another program. But
I was thinking of the previous, then that the program was very certain and stuff like that. I was just kind of curious if this was like user friendly software or is it more?
It's kind of trying to do, but it's it succeeds in some way, doesn't succeed in the other ways. You may have to go back on the time.
I'm still gonna end up having to do it again.
Yeah, so why don't we try this, just because I was looking at your design model, there were a couple interested. Why don't you try it from scratch? I know it seems like there's a lot, but when you do it from scratch,
Yeah,
it's not actually. Why don't you try that, just because I think there's some really good question going on. Okay. And then try that. I'm gonna talk to a few other people.
Wow. Okay. Cool. I was gonna say, is it okay if I just
Yeah.
Live on here.
Yeah.
And then-
I probably said to you on this.
Oh, yeah.
It's a good. Lecture recording will be up to probably.
Probably tomorrow, because these lectures are 3 hours, so it takes a while, but Zoom has to process it, so it's usually not done processing until like the meeting. So I usually do it the next morning. Yeah.
You think I can get away with it with the retweet?
Yeah, I mean, everything I did was exactly mined out in. Yeah. We're starting on Tuesday. Yeah, so everything got pushed back because this was, we were gonna do this yesterday, but because ANSYS wasn't working yesterday, I pushed it to today and then next I can do it Tuesday. Yeah. Thank you. Yep. How's it going?
I figured out what was wrong with plan.
Yeah. Okay.
The one then I was inserting the new touchscreen, and I wasn't showing it.
Yeah.
I started going to outline stream, refresh it,
Oh, okay.
and it showed like 12 of them, so why is it not working?
Oh, I see. Oh, yeah, no, those results were good.
Yeah.
At the contour you expect for, that's the deformation guy. Perfect. Great.
Notice it seems very similar from the like the Paul mesh thing when we're doing like CFDs. Is it like similar?
Yeah, no, it is, except this is a little bit easier because you can actually see the mesh.
Yeah, instead of
Just typing it up in the text file.
and hoping it works.
Training, yeah. In fact, it's probably a better first experience to that than. Yeah. Yeah, because the CFD, like, for me, I got it because I do this all the time, but your first exposure to a mesh. Yeah, doing it in the text file, kind of.
Yeah.
I think I'm a better.
Yeah, hopefully.
Oh.
I usually
I was working like hard. I did part of it. It's like.
Okay, oh, these are good. Yeah, so that's your stress, right?
I was ordered.
Yeah, so you have stress.
Just like.
Let me see your
Buy
data.
it and swap it, but they still have different.
Good, yeah, so this is great.
Yeah. I mean, so that works. The only reason that. But that just did this better. Yeah.
Oh, I know you'll have this on the first day, so if you wanna save this out, there's actually a very specific.
I needed it like same day.
Go ahead and close when you can. Yeah, but leave workbench.
It's internet, bro.
I always forget when everyone leaves. But go ahead and click on buy here. So when you actually save an ANSYS project, it's a little bit annoying, but it actually saves older. Then you try to open that in another computer, it's actually safe because it looks for very specific tasks. But if you move that folder, like all the tasks, and so what you actually need to do is you need like an hurry. But those are yeah. And so that's fine. Go ahead, make sure there's no space in the. Which one's friends? Good, save.
I wanted to do, but I didn't just try to say that far.
That's gonna create a single file. So that is like, I'm like I said.
Obviously,
Yeah, and so that's the one file. The other is there, so you just also. Yeah, so that's the one file you can upload to your Dropbox or. Right, and then when you open this up on your home computer, you can just double click that file. Yeah, so I'll go, I sort of confuse people. Yep.
That's a half hour.
Yeah. So I'm going to send you some else there. Go out.
That's the only thing. It was like.
I did sign up for the program. It hasn't actually. It's always. Yeah, so I don't know exactly how we're. Yeah. But just make sure that he knows that you're. And then once it's active, then I'm gonna bring it up.
That's all actually does.
Yeah.
Yeah.
Okay.
Yeah.
Yeah, but those 4 electives that you take your out for your. If you actually just finish your, I think that. Not just.
This, yeah, a few programs on.
Probably gonna fill out the like.
Somebody does what we work with it.
But I don't think it's actually just.
Yeah, so he's like, all right, get click with this and then. Put the system.
That's true. Yeah, so I would contact, so we're not the first one that deals with this program, I would, that's not back there, I actually always like.
I'm like, oh, what's all around? It's all works, you need to get it. You guys can get it.
Okay, good.
I have this. But it's also. And it's embassy sequel job review.
You need to contact the math department, everybody wants their email address to math office, something like. Yes, I think. They'll do single, they do those treats and things, it's a math class, so we can.
So.
But usually they accept it.
That's like everything just.
Yeah, so administratively, that's what happens, the math department
Right now. I'm I just.
you just give them your CWIT, so there's no just, is it on? Yeah, so then they'll check your TDA.
Yeah, my brother is like,
I should be good.
No,
Just think you're right now, but. Because there's so many.
I mean, granted, the math part has to, but every time this happens, I was.
Yes. Well, they say this, just say this, I'm like, I wanna learn how to design it. Yeah. But it's like.
I don't. No.
Yeah, no.
I think at this point, whatever's there is.
It's just like, that's like.
I don't know how to do.
She does it, but I wanna learn how to design it.
That's how teaching.
Now you need to set up this before and get out of there on this.
Yeah.
I don't know, it's cool.
Okay.
Yeah. I mean, I feel like I retain some things he was wanting to.
Yeah, but officially on the, it has to be official on the print.
I'm on the way to the second.
Yeah.
Okay.
Hopefully.
I know we were offering a transfer this fall.
Yeah, I'm taking.
Okay, good.
Like in second for like.
Okay.
I only need one, I'm taking this from the summer.
Cool. Yeah.
Also, one more question, Professor, the program, it's a mechanical, I know it's a stupid question, but it would, the title would be mechanical.
Exactly.
It wouldn't be.
No.
Civil?
Nope. It's just mechanical.
How does that, how does the master's?
So for our program here, our program is kind of like a generalist program. Other master's programs at other universities specialize in subject. For us, it's kind of you just get a general, just master's in mechanical engineering.
Okay, but I could always think that aerospace thing like this.
Oh yeah. So the way our masters work, so 4 of your master's classes will be. And so you need to take 6 more classes on top of that. So among those 6, you can choose whichever route.
Okay, because after this year, I think it would, depending if I take one in summer, because that's when you can take 2 classes in summer to get my bachelor's. So I'll either have. But
Okay.
You're out.
Okay.
I just want to make sure I take them.
Sure.
Thank you, Professor.
Yeah, no problem. Thank you. Yep. See you guys tomorrow. How's it going, Mo?
Oh, why? But my total deformation's on the edge.
Okay, yeah, so this is a common issue. So when you specify a result here, there's actually a geometry here. So you're actually only computing the result on that. So probably when you created this, you had that edge selected, probably when you were selecting the pressure.
Okay.
So I actually don't know how to change it in post actually. And so what I typically do is I just delete it and just make another one and just make sure that the geometry is for the whole.
Okay.
Yeah.
Thank you.
Yep.
I was like, I reran it, redid the pressure. I'm like,
I
is working.
know it's yeah, it's
I could
confusing.
go home and try to like Google it and try to figure it out. Or I could just ask you.
That tricked me for a while, and then it wasn't until like a year later that I figured out how that works.
Thank you.
Yep. How are you doing? You doing okay?
Doing okay.
Nice. Good.
Have a good night.
You do all, see you tomorrow.
See you tomorrow.
Julio, did you have any questions? By the way, Julio, I have your fluids final exam if you want to pick it up as well. I can bring it to the lecture next time you're in.